All right, welcome back. And today we're gonna continue our journey to exploring SVM. All right, so last time we defined the problem, which is to find the decision boundary. Okay, and that decision boundary should maximize the margins. And we can define the margin in terms of the distance between the decision boundary and the most nearby data points. Okay, so let's figure out, let's first go over the steps that we define the distances between the boundary and the data points that is outside the boundary. Okay, so for any data points here, we basically want to make the projection from that point to the vector W. Okay, so the W is the vector that points to that is perpendicular to the plane. Okay, and the plane is also defined by W. Okay, so the W's are the parameters that define the decision boundary, that decide the plane. Okay, so by projecting the vector from x to xi onto the vector W, right? We're able to compute the distance, okay, normalized by the length of W. So we used the special constraints that we placed at the first beginning, at the very beginning. So we say that to the nearest data points, right? So if xi is the nearest data points, then the absolute value here should be 1. Of course, it can be any constants that we define, but we let it to be 1 just for simplification. Okay, so with this additional constraint applied, then we're able to represent the distance as this quantity, this variable, 1 over the norm of W. So this is the margin of the decision boundary, and we want to maximize the margin, right? So we're tuning the values. We're tuning the values of W's. Okay, so the W can be the W is a vector, right? W in this case, if it's 2D space, then W is W1 and W2. If it's n-dimensional, then it's W1, W2 to Wn, right? So we need to tune those values within W so that this 1 over the norm of W is maximized. All right. So this is a very typical optimization problem, and it comes with constraints. So our constraints here is this one. Okay, subject to these constraints. Okay, so this I ranges over all data points. No, so the question that from Devon, that's the one is just to make the unit distance. No, there's another reason. So another reason is that so that the representations for the plane is unique. Okay, it is a arbitrary value actually here. This absolute value can be 1, can be 2, can be any constants that we set at the beginning. Okay, because it doesn't really matter which constant it is. It can be 2. If this constant is 2, then it becomes 2 over the norm of W, right? If we want to maximize the 2 over the norm of W, it's actually equivalent to maximizing 1 over the norm of W. Doesn't change the nature of the function of our objective. All right. So our constraints are like this. It's actually a bunch of inequalities. So the values of this absolute, the absolute value of this linear expression should be at least 1. Okay. So we can further rewrite the absolute value into y times this linear expression, because y, in our case, in this SVM binary classification case, we didn't use 0 versus 1. We use -1 versus 1. Okay, just for the convenience of defining our constraints. Okay, so we can rewrite the maximization into a minimization. Just take the reverse of it. We are minimizing the inner product or the dot product between W and itself. Okay, and the bunch of inequalities is simply y times the linear expression should be greater than 1 or equal to 1. Okay, and they're actually into these subjectives. These constraints can actually are in 2 cases. The first case is for those data points that are nearest to the plane. Okay, because they are the nearest data points, we know that the absolute value are 1. So to those data points, this equation is satisfied, which means their values are 1. But for the data points that are farther away than the nearest data points, then this quantity should be strictly greater than 1. All right. So anyway, we have a bunch of inequality as constraints. So we need to use the Lagrangian multiplier methods to solve this optimization problem. Okay, so excuse me, we basically need to so we need to convert the original minimization problem into some minimizing and maximizing problem. Okay, it's a typical Lagrangian duality problem. So we need to construct the Lagrangian like this, right? First, we can write the original objective here, and we write the inequality constraints into this form. We move the 1 on the right side to the left side, so it becomes -1. Okay, and then we need to put the alphas. So this alpha is similar to the lambda that we used for the single constraint optimization problem. But since now we have m constraints, okay, we have 1 to I from 1 to m. So for each I, we will have 1 alpha. Okay, so there's a superscript to alpha. So it's not just 1 alpha, it's m alphas. Okay, so having this I as the Lagrangian multiplier multiplies to the inequality constraints, and we need to have a sigma notation to sum up all the inequality constraints. And in this way, we have created the Lagrangian. Okay, so this Lagrangian introduced this additional variable, which is alpha I. And so we can put W and B and alpha to describe this Lagrangian. Okay, this Lagrangian is no longer just with respect to W and B, but also alpha. Okay, but the directions of optimizations are different. With respect to W and then B, we are going to minimize it. We are going to minimize the Lagrangian with respect to W and B. But the direction for optimization is to maximize the Lagrangian with respect to alpha. Okay, and this alpha also have constraints. So the alpha should be greater than 0, greater than or equal to 0. Okay, all right. So having this pretty complex Lagrangian constructed, we are going to go through these minimization and the maximization steps one by one. Okay, we're going to remove some terms, actually eliminate some terms, and make the whole optimization problem only depends on one variable, not on 3 variables. Okay. What we're going to do is to deal with the first minimization step, right? We want to minimize the L with respect to W and B. So what we can do, as we usually did for an optimization or for an optimization problem, is to take the derivative of the target variable of the target function with respect to the parameters, which is W and B. So if we take the derivatives of this L with respect to W first, okay? So this first term, 1/2 times W transpose times W, it is, you can think of it as a quadratic term, but it's in a vector space. It's not in a scalar numbers. It's a vector space. But basically the same principle applies to how we take in derivatives. All right. So the quadratic term is gone, and there's linear term left, and then the 1/2 is also eliminated. And also, the whole thing on the right, it's just a linear combination. It's just a linear function with respect to W, right? It's a yi times xi, right? Times alpha i plus some constants minus some constants. Okay, so the only term that is associated with W is only these terms in the square in the box here. Right. So if we take the derivative of it with respect to W, then the coefficients are the only thing that's left, which is alpha I times yi times x. Right. That's the only thing we left after taking derivatives. And to W, and also of course we want to make it 0 because we want to find the minimal point. Also for B, we'll do the same thing. B is even more simpler. Okay. Much more simpler. There's only a B here, and if we observe the coefficients associated with B, it is yi and alpha I, and everything else are gone. Okay, and then there's a negative here. Okay, so the derivatives with respect to B is like this. We want to make it 0. Okay. All right. Having these two equations available, we are able to substitute them back to the Lagrangian. Okay, back to the Lagrangian, which means the W would be this one. W would equal this summation of alpha times I times y times x, and these term will also be useful when we substitute it back to the equation. Okay, so that we can get rid of W and B, so that in the next maximization step is only with respect to alpha, not to W and B. All right, let's see how the substitution would result in. So we substitute these two expressions into the original Lagrangian. Okay, so the Lagrangian, we will get only the expression with respect to alpha. All W and B's are gone. Okay, the Lagrangian with respect to alpha is like something like this. So it's the double summation, double sigma formation, and a formula, and each item is like yi times yj, and this is the product between alpha I and alpha j, and xi transposed times xj. So there's a transpose because x is a vector. Okay, but y is a label. Y is -1 or versus 1.
Okay. Let me clarify something here. Why are there only 2 summations when there were 3 that you had at the beginning, right? So you have, when you're plugging in, I guess because it's equal to 0 on the left. Never mind.
Yeah.
Forgive me. Okay, I thought we were plugging that back in, but we're only plugging in W. Okay.
Yes. This is why it's useful, because this is useful knowledge. Well, the summation with respect to this -1 is gone. Okay, and also the b is also gone. Yeah. All right, that's how we get the Lagrangian of alpha. And also, we need to, because this one corresponds to this one. Okay? And what's inside here results in this with the -1. And of course, they can be combined. Okay. Right. And there's a summation of alpha left. Okay. And also there is a this one is gone because according to this equation, right? So all the alphas and all the W's and the B's are gone. And what we have left is something that's similar to what we call a quadratic function. Okay, because if you look at this equation, the variable, so the variable is alpha. Alpha is something we want to optimize with respect to. Okay, and all the x and y's, they are the known quantities. So the x transpose is from the substitution of w into this term. Okay, so when you place a transpose upon the vector, you basically upon the transpose outside this summation. And transpose means, well, I want to change the shape of the vector. So x is the only vector in this term, so only x will be transposed. Yeah, a and y are not vectors. Yeah, alpha and I are not vectors. Okay. So we finally get something that is a quadratic form of alpha i's that we want to maximize with respect to. Okay, so we want to maximize this this complex. Let's say let's admit it. It's still very complex. So I want to this quadratic form of alpha with some constraints. So which is alpha should be greater than 0. Okay, that is the constraints that we and also there's a constraint here. The alpha summation of alpha times y should be 0. Okay, so we will leave everything left to the quadratic programming program. It's an so there these kind of QP quadratic programming algorithms are available in most of the numeric programming languages. In Python, there's also a standalone packages that you can install to solve it. So we'll make a little bit change to make the maximization problem into a minimization problem by simply times a -1 to it. Okay, so if we look at the form of this double summation formula, this first term, okay, because there's alpha I times alpha j inside, it's actually if we rewrite alpha as a long vector as alpha 1, alpha 2 to alpha n, it'll be like this. So the whole thing can be rewrite into this matrix multiplication form. Replace the alpha here and alpha transpose here. Okay, and this summation of all alphas is the inner product between this all one vector versus the versus the vector, the alpha itself. Yeah. So I write it into this form because these matrix now becomes a coefficient, something we can write as Q. Okay, so this one is also a coefficient that we can provide to the quadratic programming softwares. Okay, so the coefficient matrix is a m by m1. Okay, and it's purely from training data. So whenever we have a training data set, we have m examples. We can construct a very large matrix by computing the products between y to each other instance, between x and each other instance. So the product between x are inner products because x are vectors. You see the first term is always transposed. Right? The first term is always transposed. Okay. All right. So, and yet we have another two constraints to subject to, which is the equation and the inequality. Okay. And a simpler form, if we rewrite, if we don't look at the details of the matrix, is that we can use Q to replace the whole complex terms. Okay. Okay. And this is a typical optimization problem that can be solved by quadratic programming software packages. Okay. So let's now focus on the results. Okay. We're not talking about how the quadratic programming algorithm solves the alphas. But all we need to use is the output from the QP, from the quadratic programming. Okay, so it should output the solutions, which is the alpha that minimizes the Lagrangian, right? The alpha that minimizes the input Lagrangian form. Okay, so having these alphas, we can immediately solve W, right? Remember when we take the derivatives of WL with respect to, the derivatives of L with respect to W, will make it 0, and that's how we get this W, right? So once we know alpha, we can plug them into this form and we can solve W. And W is exactly part of the parameters of the plane, okay? And also we need to solve B as well, right? So the B is also solvable. So we'll see. The important property of alpha is that we will find that the majority of the alphas are zeros. Although we have m alphas, which is a lot, right? But we will find the majority of them are all zeros. There's only some alpha I that is strictly greater than 0, okay? And since for those, these equations, so these conditions is always satisfied, then we can solve it in either case. For the alpha equals 0 case, this equation is automatically 0, right? And these are the data points that are far away from the boundary, okay? And if alpha is non-zero, those are the nearest data points, okay? And those correspond to the data points that are nearest to the decision boundary. And actually, it is these data sets that, it is these data points that define the margin, okay? So the points that correspond to the positive alphas are the so-called support vectors, because they support the decision boundary. They define the direction, they define the positions of the decision boundaries, okay? And that's where the name is from, okay? So if we look at the support vectors, in this case, those support vectors that lie into these positions, okay? support vectors, they're closest to the decision boundary plane. Okay, and to them, they will satisfy these equations. There's an equalization here. And to alpha, that is 0, it applies to the non-support vectors. But only for the support vectors, the alphas would be those for the support, the alpha that's greater than 0 applies to those support vectors. So actually, the summation here actually refers to, we only need to do iterates over, we only need to sum up all those values from those support vectors, right? We don't, for the non-support vectors, the alphas are 0. They just cancel out all these items. So in general speaking, the W is only defined, is just defined by the support vectors, which is the xi's here. Okay. And we can solve B by using any support vector. Okay. Because to the support vectors, this equation is equal to 1. The y times W is to 1 because support vectors are the nearest points to the decision boundary. Okay. Once we know the W and X and Y, the B is automatically solvable. Yeah. All right. So let's recap the whole process a little bit. Okay, so we basically define a problem of finding the decision boundary, right? That has the maximum margins, and we set some additional condition, set an additional condition so that the representation for the decision boundary is unique. Okay, we let the absolute value for the nearest data points to be 1. Okay. And the margin, so that we can get by project the vectors along W's direction to get the margin as 1 over the norm of W, and we want to maximize it. So it's to minimize the inner product subject to a bunch of inequality constraints. And we construct the Lagrangian duality problem, okay? And we can eliminate W and B and only obtain these Lagrangian with respect to alpha, okay? And we can input this coefficient matrix Q into the quadratic programming software to solve alpha. And the decision, and the alpha will be returned, and we can find decision boundary by looking at only those vectors, support vectors with positive alpha values. Okay, so that is the basic step of conducting the basics SVM model. Okay, so we say it's a basic model because everything is so ideal here, right? We assume that there's a decision boundary that can perfectly classify the two classes, that can perfectly separate the data. Okay, what about there's a non-linearly separable data? What about we cannot find a linear we cannot find a linear decision boundaries that do the perfect split. So this is a case that we need to refer to other methods. So in outline here, we say there's a method called kernel method. But other than kernel method, we are also going to talk about the soft margin method. Okay, so it's not just a kernel method. But we will look at kernel method first. So the example we show here is a typical non-linearly separable data, right? If we want to separate the blue points versus the orange points, there's simply no way to draw linear lines to separate them. Okay, there's always misclassifications. Okay, so what we want to do actually here is to find a way to somehow converge the original data points in the original space into some new space. Okay, so in that new space, the data are actually separable by a linear plane or by a linear decision boundary. Okay, and if we convert the linear boundary on the right, which is a line, which is a straight line, back to the original decision boundary, back to the original space, it may correspond to this circle. Okay, so we're looking for some transformation from the current space to a new space. Okay. All right. So let's see the example again. In these data points with actual values. No, this is not done during data normalization. We need to before we feed into the model, we basically want the data already normalized. Okay, so for example, in this step, the data x1 and x2, all the features, they are already normalized, right? They are already between 0 and 1. Okay, but it's still not separable. Okay, so what we can do is to conduct a nonlinear transformation, right? We can compute z1 by x1 minus 0.5 square raised to the power of 2. And z2 is also x2 minus 0.5 and square. So in the z space, in the new z space, because we got z1 for each x1 and z2 for each x2, so it's a one-to-one corresponding relationship, one-to-one mapping relationship. So in the new z space, the data looks like this. And in z space, we can easily draw a line. Okay, and this line, if we convert it back to the original space, it corresponds to a circle. Okay, so our trick is that we now use z instead of x. Okay, all right. So remember, our goal for SVM is that we want to minimize this Lagrangian with respect to alpha, right? So we can simply replace the xi's, the inner product terms here, the inner product between x and xi transpose times xj. We can replace them with the inner product in z space into the purple color z space, right? Because we have converted all the data points into z space. Okay, but the y doesn't change. Y are just labels. Right? And the alpha is not changed because alpha is the variables we don't know. We want to optimize with respect to. Okay, so this z space can actually be of higher order dimensions than x. It can have can exist in a higher order space, higher dimensional space. Okay, so for example, if x is in 2D space, right? We have 2 dimensions, x1 and x2. But for example, we can convert it into 1,000-dimensional space, z. Okay, so that the inner product is this. In z space is the inner product between 2 very long vectors. Okay, but that is okay. Okay, we need to compute such m inner products. Okay, but the number of data points m does not change with dimensions. Okay, so it means actually we have a lot of freedom. So the z space is something that we can explore with a lot of freedoms. All we need to provide is to compute the inner products in z space, right? We actually don't care the dimensionality of the z space. It can be 1,000, 2,000, 100, or 50, right? Any number. So as long as this conversion, this nonlinear transformation is helpful for us to build the SVM model. Okay, it's actually the same optimization problem, right? The optimization problem doesn't change. It's just the quadratic programming problem, right? This thing doesn't change. This part doesn't change. It's just the change of the coefficients. Okay. All right. So it's okay if the z is of higher dimension than x. All right. So this is good news for us. So this means that we can use a lot of very flexible transformations to find the support vectors in z space. Okay, so for example, the x space is like this. It seems very messy, not separable. So these data, if we're gonna draw a non-linear decision boundary, it's probably gonna be this, right? So these support vectors actually lives in z space, and this decision boundary is just a pre-image. It's like a conversion of the support vectors in z space back to x space. Okay, because in x space, this boundary is not a linear boundary, right? and we cannot in X space, we cannot draw a linear line. So this decision boundary is not a linear function in X space. It's just a pre-image of the of the boundaries in Z space. Okay, so in this case, the margin is not maximized in X space, but in Z space. Okay, but this is just a simple demo of the results of the outcome of those Z transformation. Okay, so we actually don't know yet about how to choose the transformation, right? We just know that we could do such an operation, but we don't know how yet. And now let's look at different ways of doing this Z transformation. So first of all, let's look at what we need from the Z space. Remember, our constraint doesn't change. Constraints do not change either. Okay, so there's no requirement of Z to satisfy the constraints. Okay, so if we want to solve the Z space, solve the quadratic programming in Z space, we basically it will result the alpha. It will return the alphas, and we can use the W in Z space to solve. We can use this equation in Z space to solve the W. Okay, so it's just a replacement of X with Z's. Okay, but the form is the same in X space as X space, and the B can also be solved by taking any data points that are support vectors. Okay, so the decision boundary that we get is something like this. Okay, the only difference is X to Z. Okay, so what we need to know is only here, the purple parts. We only need to know the Z times D transpose times ZK. Okay, so that is the only thing we need to know. The inner product between the data points. Okay, so we do not know exactly what the form is. Yeah, but of course, if we know the form, that's better. If we know the form, like we did for the circle transformation, right? If we know that Z equals X minus 0.5 square, then that is perfect, right? We can immediately compute the inner product. But it's okay that we don't know the form of the transformation, but we know that it is some type of inner product. That is sufficient. Okay, we just need the inner product. Just give us the inner product, and then we can solve the quadratic programming problem. All right, so let's see some examples of inner products in Z space. For example, given two data points in X space, we want to know the Z. Okay, so we can define the inner product in Z space by a kernel function called capital K in this case. This is our kernel. So a kernel is just some function applied to the 2 points in X space in order to compute some inner product in Z space. Okay, the inputs so it represents some sort of inner product between X and X prime, but it is some results in a different space, in Z space. So a concrete example, if we have X and X prime like this, if we use the second order polynomial transformation phi to indicate the transformation, then the Z can be in this in this form, right? If the Z of X becomes this. Okay, so of course the dimension of Z is higher than X. We have 1, 2, 3, 4, 5, 6, 7. Okay, it has 7 dimensions. It's a very high dimensional representation than the original 2-dimensional representation. So if we compute the transformation for Z and Z prime, and if we compute the kernel function as well, it becomes like this. The kernel function can be is a summation of all these terms. right? It's the inner product in Z space. Okay, so actually we can compute the kernels without transforming x and prime, without knowing what kind of polynomial transformation or whatever other polynomial whatever other transformation that's phi is. So we don't actually need to know phi. So this slide shows that if we know the transformation, it is good for us to compute the inner product. But we don't need to know the transformation at all. So consider this form. This kernel method, this kernel function, which is the 1 plus the inner product in x space, then raised to the power of 2. Okay, so this is a new kernel, and this is different from the previous slide. So what about it's just a function. It's not an inner product in x space, but we don't know if this is if this is the inner product in another space. So now we're gonna examine it. So what if we expand the term for x transpose times x prime, assuming it is in two-dimensional space, then we would have something like this. If we expand this term as well, it becomes 1 times this one, the combinations, and the combinations of all the x's. So it's going to be like this. Okay, so if we observe the coefficients here, this is still actually an inner product. Okay, so we can, if we use such a transformation, like if we let z equals 1 x squared, x1 squared, x2 squared, square root of 2 times x1. If we use such a transformation, then if we compute the inner product between z and z prime, we will get exactly this form. Okay, so the whole idea is that if we choose the kernel method like this, if we choose the kernel function like this, even if at the beginning we don't know whether this is some inner product in the z space, but eventually we will find that, okay, it is indeed some inner product in some space. So that means we can be more bold in choosing the kernel method without needing to worry whether this is some sort of z transformation. Okay. Yeah. So we simply need to know the by projection of the data. I mean, assume you mean the inner product of the data. Yeah. We just don't need to know the full dimensional representation in some space. Okay. All right. So this type of kernel is something we can call the polynomial kernel. Okay. So it's a polynomial transformation at order of q. So in the previous slide, we have q equals 2. So actually, we can change the value of a q to different values, to different numbers. Okay. So applying this kernel on the original inner product of x space, we can always get some new inner products in some z space. Okay, but we don't actually care about the how the transformation is done. We just need to know that the kernel method can work. Okay, so this is actually a rather simple computation. Okay, it's summation of d products and then raised to the power of q. It's not a computation at all. We don't need to actually expand the polynomial terms. Okay. So in computationally, it's rather simple because given the data, we can immediately compute the transformation, the inner product between x, between each pair of x, and then we just use 1 plus that inner product and raise to the power q. We can immediately get some kernel values, okay, in some new z space. All right, so we can further scale this, adjust this scale up, right? We can apply some hyperparameters like a, b, and q. So these are hyperparameters, which are the constants we can experiment on. So because sometimes it's not the experiments is I mean the results depends on depends on our luck. So we don't know what kind of kernel method works on some data. Maybe some non-linearly separable data, they can only be separable in higher order, in order that is higher than 3, for example. So when we try 2, it doesn't work, but we should try 3, and we can also try different A and B to see if they can result in better performance or not. Okay, so that is the polynomial kernel. And another type of kernel is called RBF kernel. Okay, we only need to know the Z space exists, but we don't need to know what Z is. So this is a very good showcase example here. So it's called a radius basis function. It's basically to use the distance, the Euclidean distance in X space as the inputs for the kernel function, and an exponential computation is applied. Okay, so the distance in Euclidean space in X space is used as inputs, and we compute the exponential term of it. So this is quite weird kernel function, but we will see that it's quite useful because this kernel function is also some inner products. If we can expand it, right? For example, we use gamma equals 1. If we expand it into this type, we have 3 exponential functions, right? And if we use the Taylor expansion for the last exponential function, we will have a series like this. Okay, we will have a series like this. So this summation of this series is something we can write into the form of inner product. If we separate the blue part, if we think of the blue part as a vector and the yellow part as a second vector, so it's still some inner product. This is still some inner product in the form of some inner product in some Z space, but the dimensionality is infinity because the Taylor expansion for the exponential function will never end. Okay. Yeah, but this is just to showcase that the RBF kernel that looks like this is valid. It still refers to some inner product in Z space. All right. So whichever Z transformation or kernel methods that we use depends on the data, right? It's not a guarantee that quadratic kernel must works or RBF kernel must works. Okay, this is very empirical choices. It's very experimental. Primarily decided by the nature of your data. Anyway, given the kernel functions, we're able to solve the quadratic programming. We're able to create a new form for the quadratic programming to solve, right? Which is the Q. Okay, remember the Q coefficients. Originally, it is purely from X and Y's. So now, because we use kernel, we should not use these simple inner products of X. We should replace the inner product between X with kernel method. Remember, we need to choose some kernel function to replace the inner products in X space with some inner product in Z space. But we don't know. We don't need to know what the Z space is. We just need to apply some kernel methods. Okay, with the kernel applied, everything else is the same. The only change is the coefficient matrix, right? Nothing else has changed. So given the quadratic programming, we're able to get some results, which is alpha. And the majority of alpha are 0, and only a handful of it maybe are non-zero. So we can use these non-zero support vectors to compute W. But here it is Z, okay? And our decision boundary is also in Z space. And the decision boundary, because the W is in this form, if we substitute into the decision boundary here, we will have the Z transpose times Z here. So actually, it is the inner product that we need to know, okay? So eventually, we don't need to know Z at all. We just need to apply some kernel methods here and use this term to solve the B's. Okay. And we are able to solve B and for any support vectors that is greater, that has alphas that's greater than 0. Okay. So the method is like this. Because we know the decision boundaries, okay, and all we need to use is to use the form as the model. We just need to know on which side the data point is at in Z space, okay? But we don't actually need to know what Z is because we just need to know this inner products, right? So based on this model, we just need to check its sign, and oops. And if it's positive 1, then we say the prediction is positive 1. If it's negative 1, then we say it's negative 1. Yeah, that's a very straightforward prediction can be made. Okay, so that is basically how kernel methods can be used to solve the to deal with the non-linearly separable problem. All right, but kernel method is a very heavy method, right? We need to support quite to experiment with quite a lot of additional hyperparameters. We need to decide the kernel. We need to tell the to experiment with the hyperparameters, right? So and this kernel method sometimes becomes just too expensive if we don't have that many non-linearly separable data, because the kernel method actually works only better for horrible in non-separable data. If the data looks like purely non-linearly distributed. But sometimes we can use soft margin to tolerate these mistakes. And another issue with kernel is that even if we applied kernel to some higher dimensional space, but it is still possible that those data are not separable in higher dimensional space. That is purely possible, right? So what about those cases? So we can use soft margin to tolerate those mistakes, to tolerate the non-linearly separable data. Yeah, that is something we're gonna use. Just be more tolerant. Just allow for some sloppiness. Okay. So the slightly non-linearly separable data means that there's some misclassifications every here and there, right? I mean these points, right? Those are slight mistakes, slight sloppiness, and often we can combine these two methods. So next we're gonna show how the soft margin actually are implemented. All right, let's look at the margin. Zoom in a little bit again. So for support vectors, we know that the support vector satisfies that the y times the linear expression equals 1. So for any data points outside the margin, we must have yi times this linear expression to be greater than 1. Okay, but for what about some inside data points? Now, because we are considering the violation. Okay, so if we allow for violations, then we actually have two scenarios. The first kind of violation is the violation of the margin, which means the y times the linear expression, this term, is still greater than 0, but it's smaller than 1. Okay, it's just smaller than 1. And the other violation is a misclassification. It's the opposite. It's the y times the linear term is smaller than 0. So of course the misclassification is a more serious mistake. Okay. So as shown in the graph, this one is a violation of the margin. while this one is a violation of the is the misclassification, right? It's on the right side. It's on the wrong side of the decision boundary. So we're gonna deal with these two cases. Okay, so what we're gonna do is to modifying the optimization goal a little bit, but including an error term. Okay, we use a slack to measure the violation. So the slack is written as this sigma. Is it called sigma? This Greek letter, or maybe epsilon? I think I didn't pronounce it correctly. Yeah. Anyway, let's call it slack. Epsilon. Okay, epsilon. So this slack term is something we introduced to the optimization goal, right? So this time we don't ask the this expression on the left to be strictly greater than 1, but we allow for some slackness, like we allow for this error, and this error should be greater than 0. Okay, so the margin, so it's actually psi. Yeah, I remember it should be psi. Epsilon is a smaller number. Yeah, epsilon is written as this one. Yeah, psi. Okay, interesting. Okay, so we can basically include this slack, this psi, into the final optimization function, and the total violation is the summation of each psi here. Okay. All right. So we basically need to minimize the original function, objective function, now plus the total errors, and this error is adjusted by the capital C. C is some constant to control the strength of the error. Okay, and our subjection, our constraints, nonlinearity, inequality constraint is also changed because that's how we introduce the slack. Okay, we want to minimize the original form plus the slack because we want to minimize the error. We still want to minimize the error, but now we are more tolerant to the errors. Okay, and the errors should be greater than 0. So now we have an extra variable introduced, right? It is no longer W and B. We have an extra psi variables. Okay, so in this term, the C is some hyperparameter that quantify the importance of avoiding violations. Okay, so if the C is very big, that means we want to, because the whole thing is being minimized. So we want to learn only small size. Okay, we want to only allow for small mistakes. If a size is small, then we are able to learn in a way that the big size are allowed. Okay, because the C is the strength of constraint. The strength of the slack is small. It's a bit similar to the L2 regularization, right? Remember, we have we want to minimize the total norm of the parameters. So that L2 term is also controlled by the lambda, right? So it's similar to that L2 sense. All right, so but now since we have size, we need to construct a new Lagrangian. We have size. So the size is a variable. For that size, we need to construct a new Lagrangian multiplier, which is called the beta. Okay, and the beta is similar to alpha, but beta is associated to the psi, not to the W's or B's. Okay, so we have now this more complex Lagrangian with respect to WB, psi, alpha, and beta. Okay, but what we need to do is to do the same thing. It's a duality problem. We need to first minimize with respect to WB and psi, but maximize with respect to alpha and beta. Okay, so we still do the same thing. We take the derivatives with respect to w, b, and psi, and we make them 0. Okay, and replace them into substitute them to the original Lagrangian term, right? Which will actually eliminate most of the terms that we don't want. Okay, which means the psi's are gone. Okay, it's exactly the same Lagrangian actually resulted in. So with this new Lagrangian, with the new Lagrangian, we will get the exact same Lagrangian, but the additional condition is that we have some additional constraints, right? The constraint is that the alpha should be smaller than c, and the beta should be greater than 0. Okay, so the alpha is no longer unbounded. Okay, but the way we solve the alpha is to use the quadratic programming, which doesn't change a lot. Okay, so the w will be obtained by having alpha first solved, and also we're going to minimize a difference objective function. All right, so the way of solving this quadratic programming is not that different from the previous solution. The only difference is that now we need to consider this different upper bound. Okay, so let's see the outputs of these support vectors if the soft margin is considered. Okay, so the margin, now we have margin support vectors, which are those that are greater than 0 and smaller than c. Okay, and they still satisfy this equation: y times the linear expression equals 1. And their psi are 0 because psi refers to the error. They don't make any error, so the psi is 0. And the beta is therefore greater than 0. And for the non-margin support vectors, they actually refers to those correspond to those alphas that are equal to c. Okay, they actually refers to they have the relationship as y times the linear expression smaller than 1, and their psi is greater than 0 because they are actually errors. Okay, and there are also two cases. One of them, for example, these 3 and 6, they simply violate the margin but are correctly classified. So this quantity is still greater than 0. Okay, it's just smaller than 1. Okay, it refers to x6 and x3. But for the other cases that violates the margin, then these are the misclassifications. And in those cases, the y times this linear expression is smaller than 0. Okay, so they are on the right side, on the wrong side. These two. Yeah, that's basically how we can classify the support vectors. But these are all support vectors. Non-margin support vectors and the margin support vector, they are all used to define the shape of the decision boundaries. Okay. Yeah, it catch the misclassifications. If you look at these quantity, if you examine the values of those quantity, if it's a smaller than 0, then it's a misclassification. So, but if we allow for such a disclassification, it's actually helping us define the decision boundaries. Okay, because sometimes if we don't allow any misclassification, there's no way to draw a decision boundary. Okay, so this decision boundary in this case is like co-decided by the correct margin vectors and the non-margin vectors. Okay, because we allow for such a slackness.
So I have a question. If you had the decision boundary be a horizontal line that's like, say, between x4, x3, and x7, just the line that's horizontal between that, it would give you much smaller margins, but it would have greater correctness. Which is more important? Yeah, like that line. Yeah, if it has larger margins or if it has more accurate results.
Yeah, so that is a good point. So if I draw this line, the margins will be smaller, but on the training data sets, I have a better performance in terms of accuracy. But it is risky because my model is going to be evaluated on some different data sets, right? I want the model also to perform good on some unseen new data points, right? But if the margin is too small, then say if I have a new data points coming in at this position, then it is more likely to be classified as yellow, right? But by observing the data, it's actually it's closer to the group of these blue data points. So a smaller margin is risky to generalize well. Okay, the smaller margin is not. I would say it has a higher risk of overfitting. So if we want to really,
makes sense. Yeah, thank you.
Yeah, if we really want to find a model that works, then we better maximize the margins. Yes, I see another question. If we have multiple classification, that's a good point. So one strategy is to use the one versus all. Like if we have three classes, A and B and C, then we can first build, we basically need to build three models. We use A versus B plus C, and we consider B plus C as a second class, right? And then we train a third model, a second model that classifies B versus non-B, and a third model for C versus non-C. So altogether, we need to train these three models in order to classify whether that has three target categories, right? So I think it's a typical solution for support vector machine models. This one versus the rest, one versus the all kind of strategy. All right. So lastly, let's talk about the margins, the hyperparameters. So there's actually a lot of default options that we can choose from. For example, the C, when we use the soft margin, the C actually ranges from these discrete values like extremely smaller values to extremely large values. Okay, so we can basically use cross-validation. That is to separate the data into different groups by finding the best Cs. Okay, and also we can combine it with kernel methods like the RBF kernel. It comes with the gamma. Gamma is also a hyperparameter, right? And we can use the grid search, which is to search over discrete choices for C and gamma. Okay, and for different kernels, we have a whole lot of different hyperparameters to choose from. All right, so we are pretty much done for SVM, and the last page is to summarize everything from the simplistic SVM model to the model that use kernel as inner products and the soft margin ones. Okay, there will be a homework for SVM, and in that homework you are asked to implement the SVM, a simple SVM model using a toy data sets. Okay, so that'll help you gain some experience in terms of understanding to understand what the alphas really mean and how to determine the support vectors and how to use the support vectors to draw to draw the decision boundaries. And yeah, that's so much for SVM. Any questions so far? I don't know, for the crazy data sets like super non-linearly separable data sets, I don't know whether we can find a theoretical best kernel. Because the kernel is to solve the non-linear separable problem, and there's in theory, there's an infinite number of kernel methods to choose from. Yeah. Do we always project into that same X space, or is it depending on the data sets? You mean the Z space, right? Yeah, depending on the data sets. Some data sets use different kernels. So different kernels actually refers to a different projection, different Z space. So once we change the hyperparameters a little bit in kernels, we are actually changing the projection. Yeah, the projection is from X to Z. The output of the kernel method of the kernel function is the inner product in Z space. All right, so if there's no questions, I'm gonna stop the recording.